Okay, and now we're ready to explore more properties of matrix norm. So if you stare at this definition of the induced matrix norm, you see that we can define what's so-called a two-induced norm by just taking the two norms over here. And similarly for the one norm and the infinity norm. However, the issue with these norms is that they're very hard to compute. Like imagine you sitting and trying to calculate the supremum over infinitely many vectors, and that is very hard to do, right? So what we're gonna do is that we're gonna try to define some equivalent definitions of the one and the infinity norms by the following theorem. So let us try to do that. So this theorem says the following. Okay, if you're given a matrix A, say that is written as Aij, then the first part of the theorem says that the one norm of A is the maximum colon sum, let me say maximum absolute colon sum of A. And what that means is that you consider, you take the maximum over all j's indexing the columns, and you sum each column, you sum the entries of each column over I. This is the first part of the statement. And the second part of the theorem is the infinity norm of A is just the maximum absolute row sum of A. And that's the maximum over all rows where we sum the row entry over J. So over here, we're fixing J, we're fixing a column and considering its sum, and then we get a number. And then we do that for every J and we take the maximum over these. So why is this important in the first place? Well, just imagine we've descended from calculating the supremum over infinitely many vectors to just summing the entries of the row, the entries of the rows and the columns, and just taking the maximums of the sums, right? This is tremendously easier, right? So let us prove this theorem. The proof isn't that bad, so let us do the proof. And the proof goes as follows. Okay, so let's see what we want to prove, and let's see how it goes. So let us denote this by B and this by C, just for ease of notation. And let's start with the first one. Okay, so if we recall what the one norm is defined as, if we want to define it as the induced norm, it's going to be the soup over all such ratios. Okay, so this is a second trick that I want to teach you here. So whenever you're faced with such a problem, what you want to do is you want to prove two inequalities to get the equality. And this is a standard trick in analysis. Now, if you look here, we have a supremum over a huge set. Okay, so what we want to do is that we want to attempt to prove that this ratio is less than or equal B for every x not being 0. Well, if we do that, recall this is the B that we're talking about. Well, if we do that, then we can then take the supremum over all these x's, and we get that the one norm of A is less than or equal to the value b that we're looking for. So we would get one inequality if we could do that. So let us attempt to do that. So let us consider a single, let's take an x, not 0, and let's consider this thing. Let's try to relate it to the norm of x. So if we could prove an inequality, something like this, then we can divide by the norm of x both sides, because we're taking x not to be 0, so the norm of it is not 0, and then we get the inequality that we're looking for. So let us try to prove that. Okay. So let's see. This, by definition, is the sum in absolute value of the entries of the vector ax. Because ax is a vector, so we just sum its entries. This is the definition of the one norm. However, I want you to recall here how we used to multiply matrix with a vector. What we used to do is that we used to say that, say this is the resultant vector, the ith entry of this vector, of the resultant vector, is just the ith row after multiplying it or dot producting it with the vector that we have. So what I'm trying to say here is that the vector ax is such that the ith entry of it is the ith row of a dot product it with x. So this is the definition, right? So, and if we expand this a bit more, we see that this is gonna be the sum over aij xj, where we're summing over j, because we're gonna be taking the ith row of a and hitting it by the vector x. So we're just doing a dot product here. Okay, so if we go on and proceed with this and just put the things in their values, we have the following, where we have here an absolute value. So now it's standard here to use the triangular inequality. So let us do that, and we get this thing. Okay, now let's recall what's the goal. The goal is to prove that this is less than or equal b times the norm of x in 1. So we want the one norm of x to appear. What's the one norm of x? It's the sum of its entries in absolute value. So let's see what the ugly term here is. So the ugly term here is this thing, because if I didn't have this one, we would have just had the norm of x, right? So what we're gonna do is that we're gonna try to isolate the xj. Let's see how we can do that. So if we first swap the sums, which we can because it's a finite sum, as such, and then if we take the xj to the sum that it's indexed by, because it's independent of I, we can do that. Okay, however, the outer sum is summing these things. These are the summands. So there is this ugly term that we want to get rid of. So to do that, what we're gonna do is we're gonna upper bound this by the maximum of all of these such entries. So what we're gonna do is the following. We're gonna take this loses to the maximum over all j's of this ugly term. And what we'll be left with in the inside of the summand just xj. So this is precisely the b that we're looking for, and this is precisely the one norm of x. So this is the maximum over like the column sums of A, and this is just the one norm of A. So if we look at the very ends of each inequality and we divide by the norm of x both sides, we get this is less than or equal following thing. But this is true for every x not being 0. So what we're gonna do now is take the supremum over all of these x's, and we have this inequality. The right-hand side won't be changed because it's independent of x. Okay, and this one is just one norm of A. So we've just gained one inequality. And to complete the proof of one, we need to prove the other inequality, which is this one. Okay, so let's see how we can do that. So here's another standard trick when you're proving such things. Whenever you want to prove that the supremum of something is equal to something, and you could actually upper bound the supremum with that thing, all you need to do is pick a value or pick a particular x that attains that upper bound. So you want to prove that the supremum of something is equal to a value. What you do is that you upper bound the supremum with that value, and then you prove that there is an x that attains that value, that upper bound. So let me try to explain what I'm saying here. So if you could actually find an x0 that is not 0, such that this is attained, then what we can do is then upper bound this by the supremum by this thing. And once we've done that, we would have gained the other inequality because this is just the one norm of A. So we would have gotten the other inequality over here. So let's see what kind of x0 we want to take. Okay, so here's what we want to do. Take x0 to be, we're going to figure it out, and we claim and here's our claim. This is what we're claiming. Okay, so let us do that. So to prove that, we need like to recall something about matrix multiplication. So if you recall, if you multiply the matrix A with EI being the standard vector where it has zeros everywhere except in the ith position, it has a 1. Then once you multiply A with EI, what you get is let's call it EJ. What you get is the jth column of A. Okay, so once you hit A with EJ, you get the jth column. So the one norm of AEJ is just the sum over the entries of the jth column in absolute value, because that's the definition of the one norm. So let me tell you what I'm trying to say here. Okay, so this value is the maximum over the column sums, right? So since we're taking the maximum over the column sums, there must be a column, one of the columns of A, that attains that value, because that's the maximum of them, right? So let's say here, take I0 to be the index, the column, with the maximum sum. which is B in this case. Okay. So once we've done that, what would happen is that let's call it J0 for sake of notation. So what we would have done is that we have that the one norm of this is just B. Okay. And we've just noticed that if we hit A with EJ, then we get the jth column back. So what we're gonna do is that we're gonna take X0 to be EJ0, so that A EJ0 in norm is just this thing in norm, which is just B as such. Cool. So now that we've done that, all what remains to show is now that we've done that, we really wanna prove this to complete the proof, but I mean, look at this. What is the norm of A EJ0 over EJ0? Well, EJ0 is just a vector with zeros everywhere except in the J0's position, we have a 1. So the sum over all these entries is just 1. So that is to say the one norm of EJ0 is just 1. Okay, and that means this is just A EJ0, which we just proved to be B, and this actually completes the proof of 1 in virtue of this observation. Okay, so we've gotten the second inequality, and we already had the first inequality, so we are done with 1. So let us do 2 now. So on to 2, let's prove 2. So let's recall what 2 is. Okay, observe that 2 is saying that the infinity norm of A is just the maximum over all rows. We're taking the maximum over I of the row sums, and we're calling that value C for the sake of notation. So let us attempt the proof again. This is 2. We're taking the infinity norm of A, and let's recall that this is just the supremum over all x's not being 0 of AX infinity over x infinity. Okay. Again, we do the same trick. We want to prove 2 inequalities. The first inequality is gained from proving that this ratio is less than or equal to C, because again, what's the claim? The claim is that this is equals to C. This is what we're trying to prove. Well, the first inequality is gained by proving that this is less than or equal to C for every x0, so that we can take the supremum and get A infinity on the other hand. And we'll figure out how to do the second inequality. So let us start with this inequality. So let's fix an x not 0, and let's try to analyze what this is. If we start with this one, and again, the goal is to prove that this is less than or equal to C times the norm of x infinity, so that we can divide by the norm of x, the infinity norm of x, and then we get the inequality that we're looking for. So let us attempt this. Okay, so if we start with this, by definition, again, what is that? Well, this is by definition the maximum of the absolute value of the entries of this vector. But if you recall what we said about this, the ith entry of this vector is just the sum over j of aij xj. This is what we've talked about over here. Due to this reason. Okay, and if we just replace back the value by itself, and if we just replace the value back, we get this is the maximum of the absolute values of these sums. And we now just use the triangular inequality to get this. And let's now remember what's the goal. The goal is to prove that this is less than or equal c times the infinity norm of x. But let's recall that the infinity norm of x is just the maximum of the entries of x. So what we really want to do is we want the maximum of the entries of x, which are xj's in this case, to appear on the right hand side. So what we're gonna do is we're gonna pull the maximum outside of this whole thing by taking the maximum of the xj over all the j's. And this loses to the maximum over j's of the xj's. And we could pull it out because now it's independent of I. And we have the following. So this is the c that we're looking for. And this is the infinity norm of x. So once we divide by the infinity norm both sides, what we get is this thing. This is true for every x not being 0. And now all is left to be done is to take the supreme on both sides, and we get that the sup over all x not being 0 is less than or equal c, because c is independent of x. We can do that. And this is just the infinity norm of a as desired, and we get the first inequality. So now the goal is to prove the second inequality. And again, a standard trick here is to pick a value where the upper bound is attained. So let us do that. So what do we want? We want to find an x0 to be something such that this something we're gonna figure it out. So such that ax0 in infinity over x0 in infinity is equals to c, attains the upper bound, because once we've done that, this will loses to this being a term of this will loses to the supremum, which is just a infinity. Okay, so if we could do that, if we could find such an x0, then the second inequality would be proven, and we'll be done with the proof of 2. So let us see what kind of x0 we can take here. Okay, so I claim that this x0 has to be the following. Okay, so again, c is what? It's the maximum of the row sums. So let I0 be the index of the row with the maximum absolute sum. In other words, we want the following to happen. We're fixing I0 and we're summing over j, and we want this is being the I0 sum of, like, this is being the I0th row where we're summing the entries of it, and we want this to be c. We can pick I0 to be such that this sum is c, because c is the maximum over these. Okay, and now before I tell you what the appropriate x0 here is, let me recall to you what the signal of a number is. The signal of a number is just it's itself divided by its absolute value when it's not 0, and it's 0 otherwise. Okay, and also recall that if we hit a number by its signal, what do we get? You can see it from here. Like if we hit it by its signal, what we get is this squared over this, the absolute value of it, and we'll be left with the absolute value of it if it's not 0, and with 0 otherwise. And also recall that, or observe that, if we take the absolute value of the signal, what we'll have is the following. We'll have the norm of z over z, or the absolute value of z over z, and that is 1 if z is not 0, and 0 otherwise. Okay, that is cool. All of this is to say the following. Okay, recall if we have ax and we're taking the ith entry of it, this is just the ith row after hitting it with x, after taking the dot product with x. Okay, so if you look at this, what you're gonna see is that okay, and now let's observe what happens if we take x0 to be the ith row and let's observe what happens if we take x0 to be the signal of the vector ai0, the vector being the i0th row of A transpose, and this is just like the vector where we're taking the signal of each entry. So we'll be taking the signal of the first entry, the signal of the second entry, and so on. If we take this particular vector, and again, there's nothing like special about this vector, and you might ask why we're choosing this vector. Well, we're choosing this vector because it's the vector that works, that actually gives the right answer. Okay, and now let's see what is the norm of ax0 in infinity, because recall the goal here is to prove that this fraction is equals to c. So let us try to analyze what this and the norm of x0 is. So let's analyze what the infinity norm of these two vectors are, because we want to consider the ratio of these. Now, given that if you look at the infinity norm of x0, you will see that it's the maximum of the entries of x0 in absolute value, and that is just the maximum of signals. Let's use a j here instead of ai0 j in absolute value over j. But we've just seen here that the signal, the absolute value of a signal of a number is 1 or 0, and we have therefore this is equals to 1. So okay, and now since we have that this ratio is therefore this norm divided by 1, which is itself, therefore, we only need to show that this is equals to c. Okay, so let us try to prove this. If we take ax0, it's going to be the maximum over J of AX0J, taking the maximum of the absolute value of the entries, and we really want to show that this is equals to C. Okay, and recall what is C? C is the sum of AI0J over J. C is the maximum of the absolute sum of the rows, and we've picked I0 to be that row with the maximum value. So all is needed to show now is that this maximum is equals to this. So let us see if that's true. Okay, perhaps the indexing by I is better here, so let us do that. Okay, and if we look at the ith entry of this in absolute value, that's gonna be the absolute value over the sum of Aij x0j, and this loses to, by the triangular inequality, to Aij x0j. And now let's observe that this also loses to the infinity norm of x0. Why? Because we can, well, the infinity norm is the maximum of these, and we can pull it outside by taking the maximum. Hence, we have the infinity norm of x0, and all is left in the sum is this thing. But observe that this is just a row sum, right? And C is just the maximum of these row sums in absolute value. So this is less than or equal C. Why C? Because we've just shown that this is 1. Okay, so we've just shown that this is less than or equal to C. Okay, so we've gotten one inequality, and the other inequality is trivial because it is obtained at I0. Therefore, we get that this is just C, and hence, since the infinity norm of x0 is 1, this is the same as this one, and this is less than or equal the infinity norm of A as we've seen, and this gives the other inequality we're looking for, and hence completes the proof.